said no. I can, but don't be shy or you will.
All right, I'm speaking now. Does anyone? If you can't hear me, raise your hand. All right. Thank you all for coming, and thanks to the school for inviting me to speak. I've been looking forward to this quite a bit. Before I start, I want to acknowledge and thank my colleagues, without whom today I would have very little to talk about. And so, thank you to them. As a brief overview of my talk, first I'm going to talk about what it means to attend a meeting and relate some results from a survey of Midwestern and Western secondary mathematics teachers with regard to an assessment instrument that we're developing having to do not with teachers' performance, but rather having to do with the meanings that they operate by. And I won't say anything more right now about that because to make it meaningful, I'll actually get into what we, the kinds of questions that we've asked. In the second part, and I'll say, and with the results of that survey, I think, are important for us in thinking about undergraduate mathematics education. And in the second part, I'll describe a calculus course that we've designed specifically to address the issue of attending to students' mathematical meetings and addressing the meeting, starting with the meetings they have, and having clearly having stated clearly the meanings that we would like them to have at the end of the course, the meanings and ways of thinking. As any good math talk does, I start with a math problem, okay? So I'm going to share with you a function. It doesn't have an elementary antiderivative, but it has an antiderivative. And the problem is to name one. Now, I'm not going to actually talk about that. I'll come back to this later, all right? But if you want to think about it in the meantime, be my guest. All right, so the first part of my talk is about secondary mathematics teachers' mathematical meetings. But I'm talking about secondary mathematics teachers' mathematical meetings so that I can talk about meetings, mathematical meetings held by students while they're undergraduates taking mathematics courses in a math ed program or in a mathematics program. The program doesn't matter. They take their mathematics from us in a department or a school of mathematics. So here's an example of a question that we asked. Well, this is not the question yet. A little bit of background. In many questions that we asked having to do with proportionality or rate of change, teachers used the word over, and we couldn't tell what they meant by the word over, like something changing over some period of time. Did they mean during? So this is the question we asked. Here, what does the word over mean in this context? Well, we were hoping that it meant during. Okay? And then we asked them to express the textbook statement in mathematical notation, and hoping that we would see something like this or that, but somehow showing a difference between an amount now and an amount then. So here's an example of an answer that we got. Clearly, the word over to this teacher triggered divide. Okay. This teacher had a Bachelor of Science in Math Ed. Okay. Here is one who said, well, there's something between the mass and the time, but then expressing it, again, as a quotient. So, and this teacher had a Bachelor of Science in Mathematics. So what we what we do with all of the items on this assessment, we we create levels into which we put responses. So with part A, if the teacher wrote, "I don't know," or wrote something that we couldn't interpret, then it went into level 0. If they responded that over means division, we put them into level 1. If they were ambiguous, they fluttered back and forth between during and division, we put them at level 2. And if it was clear that they were saying that over means during, we put them at level 3. With regard to part B, this is what the criteria for putting responses at level 0. Level 1 was they clearly wrote a division statement. Level 2 was that they wrote something like the change in mass equals 4, but they didn't actually represent the change in mass. Using the information that the mass of this object was given, the culture was given by the function f. And at level 3, then that's where we put responses that clearly showed a difference. So here's what we saw overall. Okay. If we just look at the rows, which tell us responses to what does the word over mean, then we have 37% of the teachers saying that over means divide, or something that we couldn't interpret. And 62% of the teachers either confounded over and division, or said clearly that over means during. But what I'd like to point out, though, is that when you look at what they actually wrote for a mathematical expression, it was a different story. So this is what I mean by attending to their meanings. Had we just answered part A, we would have said, for 67% of the teachers, we would have said, oh, okay, there's no work to be done here. They think of over in that context as meaning during. But when you take into account what they mean in terms of how they will express what they mean, then what we get is that 62 teachers did say over means during, but they either wrote a nonsensical expression or a ratio to show how you would represent that statement mathematically. Now, we're doing this because of its implications for teaching. That was the original proposal to NSF, but what we found out by giving the assessment was this has implications for undergraduate mathematics education. And I'll come back to that. So if we look at those teachers who look at A3 and B2 and B3, and we see very few teachers who have consistency between what they mean linguistically and what they mean mathematically as to the way that the meaning of over in that context. And if we look just at Bachelor of Science and Mathematics teachers, again, it's just two out of how many? 2 out of 25. Two teachers out of 25 who have coherence in their linguistic meaning of over and their mathematical meaning of over. And in Math Ed, the same story. But here is 2 out of 37. And others, what we mean by other is people who are teaching high school that have a degree other than mathematics or mathematics education. So here, what we did was we combined the two. There are combined responses to Part A and Part B, and we have a criteria for putting the combined responses into levels. And you can see that 92% of the math and math ed teachers are at a level that shows highly inconsistent ways of thinking about this word over. Now, you might think, so what? Well, it's, as you'll see, this is not an isolated instance in terms of foundational meanings not being what you would want them to be if you're an instructor and involving derivative, and this is the way that people are thinking about change over time, for example. Here's an item having to do with function notation. It's just simply to evaluate this function that makes references to other functions. Okay, overall, about 75% of the teachers did this correctly, and those who did it incorrectly, many of them it was what we called incorrect. Many of them did things like try to expand everything, right? Try to write h strictly in terms of one variable. Now so we would think that things are, they're not as good as we want them to be, but they're not horrible. So here, we went a little deeper on the teacher's meanings for function notation. So here I'm sharing with you another item. This one we gave to 111 teachers in the summer of 2000. No, we didn't give this item to 111, but we gave the assessment to 111. But not all of them saw this item. So here's the question. Okay, here's the third function C. Put the correct letter in each blank so that the function C is properly defined. All of you looked at that, and I'm sure you immediately said, well, V has to go there. Why are you even asking this question? Well, let me show you why. Of the 37 teachers who saw this particular item, 10 of them said V belongs there. 19 said R and U belong in those blanks. Now, what does that look like? Well, they said that you have to put R in the blanks for Q and U in the blanks for W. Now, I'm sure you're looking at that and saying, well, that doesn't work. Well, it wasn't so much that we were wondering whether what they say works or not, but rather what it reveals about their thinking. So, and if we look at teachers who taught more than pre-calculus, pre-calculus or above, pre-calculus, calculus, or differential equations, there were 10 of them, and 3 of them put B's. So the way that we looked at that was that it was consistent with thinking about function notation idiomatically. Idiomatically meaning it doesn't matter what's on the left side, that's just the name of the function. The whole thing is the name of the function. And then what's on the right side is what matters. So in the summer of 2013, we tested that hypothesis. We added a part B to this item, where James did what many students do, and they put one variable, they used one variable as an input variable, then use a different variable in the function definition. And we asked the teachers, according to James' definitions, what's f of 9? Now, if they're thinking about function notation idiomatically, then they'll ignore the left side. What will they get? How will they answer that question? 45. So level 0 is that they answered 45. Level 1 is that they answered, that they confounded the two somehow. Or that in part A they used both V and R and U, or something like that. And level 2 was consistency. They put V's in the slots, and then they also said, hey, this isn't properly defined. You can't do it. Now, I don't, to tell you the truth, I don't know why I boxed those, so I'm guessing. Here's another item that we asked. So the function h is strictly increasing. H of b minus 5 is 9 for some number b. which of B9 or B minus 5, 9 is on the graph of y equals h of x minus 5? Now, the way to think about this is that you put in a value for x, and when you're graphing, you will graph whatever h of x minus 5 is together with your value of x. However, if many students think that what matters is the number that h gets, so they confound the idea of input and argument. So if we think of b being a value for x and 9 being the output, then of course b9 has to be on the graph. So here we see that in the summer of 2012, 41 teachers saw this item, and 16 of them put b, and 13 said b minus 5, and then the rest said other things. You might wonder, what is this? Function name is multiplication. Well, here's what it means. You see now why we call it function name is multiplication. All right? This teacher had a Bachelor of Science in Mathematics. Here's another one. Again, in this case, they solved for h. Solve for h said, well, when b is 6, then h is 9, so it works, therefore b9 is on the graph. We almost counted this right until we actually read closely what they wrote. Okay, this teacher had a Bachelor of Science in Math Ed and taught calculus more than 15 times. So one question that you might ask is, how is that possible? If this is the way that the teacher's thinking about function notation, how are they teaching calculus? Well, it could be that any meaning for function notation is irrelevant to the calculus that they teach. If all they're teaching is rules, then an understanding of function notation doesn't even come in. You can always work around it just by focusing on conveying rules. So in 2013, we turned that item into a multiple choice item, where each of these options actually comes from something that a teacher wrote the prior summer. So we didn't make these up. We used what teachers the prior summer wrote. Okay, this is the one that we counted at the highest level. Okay, notice that it's not only which of the two are on the graph, but it's also why the two are on the graph. Okay, if you'll notice also, number 3 goes with function name is multiplication. Okay, so I'm not going to break it out by major because I want to leave the responses there, and I don't need to because the results were largely independent of major. So 24% of the teachers selected number 1. 6%, 2. 5%, so 500 teachers selected function name as multiplication. And these are all high school math teachers. 8% selected 4, and 46% selected 5. This is almost identical to what we saw in the pre-response the summer before, which tells us that this multiple choice item works. Okay, we're getting at the same thing as we would, and it's a lot easier to score. Okay, so I've just given you, we actually have 41 items. Some of them are animated items, which themselves are quite interesting. And I'm not going to share those with you, so I just want to give you an example of the way that our method, our approach to determining the meanings that teachers are operating by. So I've focused on function and function notation. So we covered areas of function notation, function of models, rate of change, etc. In all areas, a majority of teachers who took substantial undergraduate mathematics showed weak meanings like those I've already demonstrated. So it seems reasonable to conclude that these are meanings that the teachers had when they were undergraduate students. Because I don't think that they learned it by teaching. I think that's a hard argument to make. We have not done a survey of undergraduate students. Well, not a survey, but we've piloted with undergraduates, but nothing that I can share data on. So we have to wonder what sense can someone with the kind of meanings for function, function notation, etc., what sense can they make of the undergraduate mathematics? And I'll come back to some questions that I have about the ways in which a school of mathematics, or a school of mathematical statistical sciences, or department of mathematics, the kinds of issues that I believe need to be addressed specifically and seriously with regard to attending to the meanings that our students have in our undergraduate. So now the second part of my talk is about a redesign of calculus that addresses teachers' mathematical needs. I mean, students' mathematical needs. And I'd like to thank Mark Ashbrook, Stacy Musgrave, Cameron Byerly, and Neil Hatfield, who worked with me on this project. So the course is structured around two fundamental problems. What we tried to do is we tried to give the course an intellectual necessity, so that the course is about something that we can say at the beginning and keep saying throughout the course, that this is what the course is about. The first is that you know how much of a quantity there is, and you want to know how fast it's changing. The second is you know how fast the quantity is changing, and you want to know how much of it there is. But the first is clearly goes with the work that is normally done under the heading of derivative, and the second is done under a heading that is normally called integration or integral. But this also captures the fundamental concept of differential equations. You know how fast something is changing, you want to know how much of it there is. So, in terms of objectives, high-level objectives, we want students to develop ideas of calculus meaningfully and coherently. But we also want them to develop an overall appreciation that mathematics is a coherent system of ideas and methods and ways of thinking. And that there's a reason for the ideas. The ideas of mathematics do work. They solve the problems. Coming up with a way to think about continuity solved a lot of problems that mathematics was facing in the 1800s. So the course is in two phases, and I should say, okay, I have all of this in a handout that you can pick up afterward, and also I'll give you a URL for my presentation, which is online. So phase one focuses on accumulation from rate of change. And in that phase, at the beginning of the course, we address specifically ideas and ways of thinking that are absolutely essential for understanding the calculus meaningfully. Many of them are ideas from middle school, and the students come to calculus without them. And I'll go into that in more detail. So, and they have impoverished concepts of function. We work on that. We build on that to talk about approximate accumulation functions from exact rate of change function. An exact rate of change function is a function whose value gives you how fast something else is changing. And from that, an accumulation function is, so how much of that quantity have you accumulated up to that moment in time, if you like, when all you know is how fast it's been changing. That's all you know. And then exact accumulation functions, well, that's the integral. And in phase two, we turn around and we say, okay, now we've got exact accumulation functions. We've got functions that give us how much of something there is. And with knowing that function, we want to know how fast is that accumulation changing. So in phase one, okay, we look at relative magnitude correlation and linearity as a coherent system. Okay? So quotient is a measure of relative magnitude, covariation, tracking the values of two quantities simultaneously as they vary. So quotient is relative magnitude. What we stress is that when you have two changes and you want to know how large is one relative to the other, well, that's what a quotient tells you. That's what the result of division tells you, that something is so many times as large as something else. With covariation, we want them to think that variables vary. Okay. I understand that eventually you don't want them to think about variables varying, but in calculus, you just cannot get past the idea that variables vary. So let me show you an illustration here. So what I have here is just two magnitudes that vary together, one of which is always m times as large as the other. Okay? This is proportionality. And when we take into account that one of them might have a starting point, then all we can emphasize is that it's the changes in the quantities that are proportional. And then if we just do a little convention, adopt a convention that we think, we put the variation together, but keep track of them in this way that through Descartes' genius we have today, we get covariation, where we have a method of keeping track of two quantities' values simultaneously as they vary. And if we then think about a graph as simply a bunch of points, each point showing a state of the covariation. Each point has coordinates that show the values of the two quantities simultaneously. So this is a way of thinking that we work on early in the course. And then we also ask them to think about actual quantities. So in this particular case, we have a bottle that's filling with water. Okay, the height is changing at the same time the volume of the water is changing. And what we want them to do is to sketch a graph that captures the covariation of volume and height. So that each point on the graph shows simultaneously how much qualitatively the volume of water in the glass at a particular height. When they sketch the graph, then they can compare it against an actual graph. And then we can also ask them to predict different shapes of bottles. Do the same thing. The idea is to have students reason concretely about the covariation of quantities and graphs showing a record of that covariation. Another is, again, this now it's covariation, we're bringing in ideas of rate of change. So here's a scenario that the students find humorous, or some of them find humorous. So we've got a basketball that's powered by a stuttering rocket engine. The engine accelerates the ball and bursts. It just goes like that. And so that what we say is it changes velocity instantaneously, and then between bursts, it rises at a constant speed. So the ball's rate increases 1 feet per second with each burst. So here's what it looks like. Okay. So this is a graph of the ball's speed. Each half second, the ball's speed increases by 1 foot per second. So we ask students, imagine what the ball looks like as it's rising, as it's doing it. Like this. Now imagine the graph of height, the basketball's height above the ground relative to the number of seconds that it elapsed. Like this. So again, what we're trying to work on here is helping them develop a way of thinking, a way of imagining, a way to envision things that that we want them to see the mathematics described. And then we represent symbolically the distance that the ball has risen in relation to its speed at each moment in time. Then get away from the image, introduce summation notation. So that now when we introduce summation notation like this, we want them to look at that and see the basketball. So they have to think about what each of these terms mean, what the summation means. So it all focuses on reading notation meaningfully. Then we ask the question, well, suppose that we wanted to define a function that gives the ball's height at each moment in time. Not just where is it after 11 seconds. Where is it after X seconds? How high is it? Well, we have to have a piecewise defined function. Within the first interval of time, when when the value of X is within the first interval, that's the ball's height. When the value of X is within the second interval, that's how you would compute the ball's height. So the idea is that, the ball's height, you can actually compute it by looking at how high has it gone in the previous completed intervals. Time is out here someplace. There's some number of completed intervals. How far has it risen in those completed amount of time? And then you add on how much it's risen in this partial interval of time that it's now in. Now, this is done very purposely because one of the things that this shows is that if we ask how fast is the distance changing at any moment in time, the distance is changing at the rate that it's changing at a particular interval of time, and the interval in which it's changing. Completed intervals are done changing. They're not going to change anymore. The only change that's happening is within the current interval. And the rate at which the height is changing in the current interval is right there. So this is the seed of the fundamental theorem of calculus. The rate of change of the accumulation is the rate at which the accumulation changes. And that is the value of the rate of change function that you started with. So then we have we want to move to functions that change continuously, that have a continuous rate of change. So here, I don't know if you can see it, it's probably too small. But the R sub f, that's the rate of change of the function f at x. X is elapsed time, the number of seconds of elapsed time, is cosine of x. What we want to do is create a function that gives the accumulated displacement as a function of time. But all we have is its rate of change, how fast it's changing. The idea is that we can simply use the method that we use with the basketball, except that we have to take some intermediate steps. So we have to think about time being cut up in chunks, and we have to think about the ball's velocity being constant within those chunks. Now remember, the aim is to actually compute. We want to come up with a function and define it that actually computes. So now we ignore the original function. And if we knew how to compute the velocity at a particular value of x, then we could use the method for the basketball. So as time elapses, then we would do just as we did with the basketball rocket method. So the problems that we need to solve are to approximate an accumulation function for the ball's total displacement. In effect, we have to determine how many completed delta x intervals for a particular value of x, and how far through an interval is the current value of x. If we know that, then we can move forward. So if we think about this as time's passing, but it's passing through chunks of time. And so you have completed, what I've called here completed variation, and ongoing variation. Okay? What we need to know is how do we calculate, let me stop this. What we need to know is how do we calculate the left end of the interval that the value of x is currently in. Well, this gives us, sorry, I can't point at it because then I go above the movie and it gives me the control point. So the left end point of the interval that x currently is in is simply a plus the number of completed intervals of size delta x between the x and a. Okay, that's the floor function. So it's the greatest integer less than. So x minus a divided by x gives us the number of completed intervals. The floor of that gives us the number of completed intervals. Multiply that by delta x, and you get how much that change is, and add it to a, and you get the value of the left endpoint of the interval that you're in. Now, how is it that we use that? Well, because now what we can say is that we're going to use the velocity function so that for every value of x within an interval, we're going to assign the velocity at the left endpoint of that interval. And that's how we get the velocity step function. Then we can add up all the completed intervals of change. This is just like what I did with the basketball rocket. And then add on the part that is still changing. How much of the current interval have we gone through, and how much change has happened because of changing at a particular velocity. So this is the rate of change within the interval, and that's how much change has happened within the interval. So we get a completed accumulation and an ongoing accumulation. Okay, so what I have here, okay, is what I just showed you. That's the function that I just showed you. This is in a graphing program. I'm using the program that the students use. When the students solve problems having to do with accumulation functions, they would type into this program what I have here, or something that they think might get it. You know, at the beginning, it doesn't get it. And they can see that it doesn't work. So what I have here is, okay, the rate of change function is cosine x. What I'm graphing is that accumulation function. This is the accumulation function, where a is 0. I could make a negative, and that's the accumulation function. What we're getting here is the graph of that function. Okay. Every point on that graph tells us how much displacement has accumulated with a certain passage of time. So now if we go back to the original setting, and we ask the question, suppose delta x is so small that making it smaller has no practical effect. If that's the case, if delta x is so small that it has no practical effect, then we use this notation. And that's what this notation means. This notation means that we're looking at an accumulation in little bits, and making those bits smaller doesn't really matter. When that's the case, then we use this notation, and we call this the closed form accumulation function. So this is a new notation for an already formed idea. It's not a new idea, it's just a new notation that expresses the condition that now we're talking about changes in the argument that are so small that it doesn't matter. All right, so notice here, I have the same situation, but now I've represented the accumulation. The closed form accumulation. And I'm going to graph that accumulation function. Again, this is notation that students will enter into this program. So they will enter an integral as a function in order to model some situation. And then they'll graph that function to see whether or not it actually provides a good model of the situation. And again, I can vary the value of A. And one of the things that we don't spend a lot of time on it until later, what's going on when we vary the value of A? Why does this change the way it does? So in this first phase, okay, there's very little in terms of symbolic technique that we teach. The main goal is that students conceptualize accumulation functions and how to represent them, and how to reason with those representations. So, and the use of an accumulation function is in modeling a situation. Now, I want to point out, in nothing that I've shared with you have I mentioned area. Okay? In the way that we do introductory calculus, an integral does not give you an area. It gives you an accumulation of a quantity. Sometimes that quantity can be area. Most of the time, it's not. This actually solves a big problem that exists among students taking calculus, where they really fundamentally don't get how an area can be a distance, or an area can be a force, or an area can be an amount of work. Or, it's a mystery. And so they just, okay, fine. You want to find any of these things, find an area. But there's no intellectual connection between finding an area and answering whatever question has been posed. So phase 2 is rate of change from accumulation. The main idea is that we have to reconceptualize what we call amount functions. So an amount function is any function that gives you an amount of something. What we want them to do is to think about amount functions as accumulation functions. As the value of x varies, each value of x gives an accumulated amount of this quantity. Why is that important? Well, because then, if it's an accumulation function, it comes from a rate of change function. So we necessitate the idea of rate of change, the deep meaning of rate of change, by saying, look, if this is an amount function, if this is an accumulation function, then there's a rate of change function there somewhere that it came from. The question is, what's the rate of change function? And what's the initial value given a particular function, a particular accumulation function? Okay. So we're looking for a rate of change function that will give us the accumulation function that we start with. So you see, we're still in the same arena. We're still talking about accumulation functions. But now we've turned it around. Now we know the accumulation function in closed form. And we want to find out what rate of change function does it come from. So we one of the things we have to do is we have to reconceptualize average rate of change. So here's the way that we do it. Average rate of change of a quantity B in relation to a change in quantity A from A to H is, it's a constant rate of change. It's a constant rate of change that will produce the same net change as actually happened in the original function. Okay. I don't know if you're there yet, but I imagine that eventually you're going to ask why. Why have this complicated meaning for average rate of change? Well, there are three reasons. Coherence is forward-looking, and it ties the meaning of average rate of change to the meaning of linearity. So let's look at this issue of coherence. Okay? We've got a function, we've isolated an interval. We do the standard thing that you find in any calculus textbook, and you draw a triangle. Okay? And you label one of them h or delta x or something, and the other f of a plus h minus f of a. Okay? We think, okay, it's all right there, right? Well, what happens is you drew a triangle, and students think you're talking about a triangle. So the most important thing about a triangle is its hypotenuse. Everybody knows that, right? The problem is the hypotenuse of a triangle is a geometric object. It doesn't have anything to do with functions. And so you've got this disconnect between this thing that we want them to reason about. The students have a disconnect between the things you want them to reason about and the way they're reasoning about the thing that you're showing them. They'll often point to that hypotenuse and say, here's the change in the function, and they'll run their finger along the hypotenuse. That's not where we want them to see the change in the function. However, if we think of a line through those 2 points and emphasize that that line is the graph of a function. It's a graph of a function. Well, let me go on, okay? So it's a graph of a function that has a constant rate of change, and it has the same net change over that interval as the original function. So we emphasize this complicated, quote, complicated, meaning for average rate of change, so that when we're talking about an average rate of change, we're talking about the same kind of animal as we're starting with. We're talking about a function. We're talking about a function that has a constant rate of change. And so, and if you want to actually calculate that constant rate of change, that's how you do it. So you see, this is not something like, oh, find the slope of the line. The slope of the line tells you something about a derivative or something about an average. But they still think that average rate of change is add them up and divide. So we work really hard against that. I have a function graphed in polar coordinates. What does a secant between those 2 points look like? Should I draw a straight line? I'm not going to put you on the spot. I just want you to think. Well, let's think about changes, all right? Okay. There, I've shown the change in the angle and the change in the radius, right? Now, according to our meaning of average rate of change, we need a graph of a function that has a constant rate of change, that has the same net change over that interval. So, there it is. And it turns out, if I show you, well, it's kind of complicated. But this is the rate of change. It doesn't matter whether you plot it in polar coordinates or rectangular coordinates or logarithmical coordinates or whatever. That's the rate of change that you want. Now, what we would like to do is create closed form rate of change functions for accumulation functions. So we investigate the behaviors of rate of change functions in open form, and then we imagine that h is so small that making it smaller has no practical effect on the values of the rate of change function that we're defining. And then we just use algebra and what I call limit-like thinking, but we don't emphasize limits, to develop a closed form representation. We call it f prime. And then we look at, along the line, we look at under what conditions does g prime fail to have a value. So we look at super wrinkly functions. Functions where no matter how much you zoom in, it's still wrinkly. Meaning that the idea of a well-defined average rate of change doesn't happen. Okay, we look at functions that have unbounded average rates of change for small value of h. Functions that have a point discontinuity. And we look at functions that have ambiguous average rates of change. Okay, if you make your interval small enough, then it looks like you could have two different average rates of change, and there's no way to pick between them. And so we call that the ambiguous case. Okay, it's not well defined. The average rate of change is not ambiguous. So when we develop rate of change functions from accumulation function, it, on the surface, it looks very standard. But none of the meanings are standard. What we're looking at is rate of change functions that we can use to recover the accumulation function that we've got. It's always in that context. The other is that the open form rate of change function is the trusted definition. What do I mean by trusted? Well, I define R sub g, and we can graph it. And then when but we also ask them to use the rules that we've developed to, I skipped over those, didn't I? So then we use the rules that we developed to come up with a closed form definition for this rate of change. So what do you suppose one of the first things is that they'll do? Right? Oh, not me. Okay, so this is the graph of this open form of the rate of change function for g. Here is a closed form. It doesn't match. Which one should we trust? They don't agree. Which one should we trust? Well, we teach the students to trust the one that comes from the definition. So this is the one that they trust. And if instead we do this, whoa, what happened, right? Well, look, they coincide. So that tells us now, that gives us confidence that our closed form representation of g's rate of change function is okay, because it matches what we get from the one that we trust. So let me put this into a little broader context. So we have an accumulation function. It's therefore the form, an integral of some rate of change function for some rate of change function in some number a. We asked what is the rate of change function and what is A. So when students find a derivative, this is the intellectual context in which we're always finding derivatives. When they find a derivative, they're understanding that they're finding a rate of change function for an accumulation function. So they know something immediately. That this rate of change function goes with the accumulation function we started with. So the integral of that rate of change function gives us the function that we started with. We're starting, this is forward-looking. What we're doing is we're helping them develop a tool bag of antiderivatives and a way to think about antiderivatives. When you find a derivative from an accumulation function, now you know a relationship. Okay? So there, by going through and finding the rate of change function for that particular function, now we know something that we didn't know before. That the antiderivative of 2.5 sine t, etc., is what you see on the right. Also, as they develop rules for how to handle things like the sum of two functions, then we get ways of thinking about creating antiderivatives for more complicated functions. So, and the whole thing, the thinking behind it is that if you have an accumulation function, then it's an integral of a rate of change function. And if you determine the rate of change function, then you know an antiderivative. So we don't wait to talk about antiderivatives. We're doing this every time that we find a way to find a derivative. We're saying, hey, look, now we know something that we didn't know before in terms of the relationship between accumulation and rate of change. So in terms of the fundamental theorem of calculus, so we, phase one builds accumulation functions from rate of change functions. Phase two builds rate of change functions from accumulation functions. So rate of change functions are the springboard for accumulation functions, and accumulation functions are the springboard for rate of change functions. Okay, and here's how we solidify the fundamental theorem. I'll just give you some sample problems. Okay. All right, this is the one I started with. This is the one I opened my talk with. There's an antiderivative of little q. It's a function. And its rate of, and q is its rate of change function, right? Capital Q even has a graph. It's a function. So it's a function just like any closed form function is. It's just that in this particular case, we don't have a closed form representation for it. Okay, I'm gonna skip these. So we have them investigate this question, and it just turns out that varying the value of A varies the constant that you add on to any one of the family of antiderivatives. I'm going to skip past these two. They'll be in my talk online, okay? Well, it won't be online, or the digressions to use the graphic. So to reiterate, phase one builds accumulation functions from rate of change functions. Phase two builds rate of change functions from accumulation functions. Rate of change functions are the springboard for accumulation functions, and accumulation functions are the springboard for it. That's the fundamental theorem of calculus. So the fundamental theorem of calculus is built into this course from day one. It's present every day, and it's at the heart of every major idea. So we don't go, ta-da, here's the fundamental theorem of calculus, at a moment in time when students can't figure out, so what's so fundamental about it? I already know what to do on any problem you give me. It doesn't help me at all. And they ignore it. Because it's not fundamental to the calculus that they know. But it's fundamental to the calculus that they learn here. So let me come back to the issue of meaning. Okay. So students create mathematical meaning by making connections among mathematical ideas. by using those connections and the reasoning repeated. If they don't use connections they make, then those connections don't stick, and meaning doesn't develop. They also have to develop an orientation to create meaning and to reason with it. If they don't have that orientation, then they won't use those connections repeatedly. That comes from developing the orientation to reason meaning. So here are some common misgivings that we've come across. You have to sacrifice coverage to teach for meaning. I say not true. We cover everything that a standard Calculus 1 course covers. We cover it more meaningfully, and we hope, with future funding, to demonstrate that they come out of this course understanding more, but also being just as skilled as you would want them to be. Also, you can look at other examples where coverage is not sacrificed by emphasizing meaning. Marilyn Carlson's pre-calculus project, Kyung-Ha Ro's advanced calculus here, Sean Larson's abstract algebra at Portland State, Gershon Harrell's linear algebra, Chris Rasmussen's differential equations. These all exemplify approaches that emphasize the construction of meaning and having the mathematics be grounded in the meaning that is built. Another misgiving is such courses are too difficult for students, perhaps, but not because of the reasons that you might think. They're often difficult for students because of the dispositions that they bring to your course. They expect, when they sit down in a math class, they've already known, if they're a freshman, then now they've spent 12 years coming to know what happens in a math class. You memorize. Okay. Well, if they're now in a math class where that's not the name of the game, it's rather building meaning and using meaning, then there is going to be a period of profound disequilibrium. And you as an instructor have to be aware of that, you have to anticipate it, and you have to support it. You have to be a cheerleader almost. But it's not just cheerleading, you have to actually actively design your course to help them construct meaning when they're confused about what is it you're asking them to do. Another misgiving is such courses take too much of an instructor's time and require too many resources. My claim is they don't take any more time than preparing a very thoughtful and careful lecture. Where they might require more time and more resources is in supporting the students. And that you must do because if the students aren't supported, if they don't have some place to go to work through confusions, if you can't hear the misconceptions that they're working with, then it's gonna be harder for it to work. Especially given the students and where they come from. That's what makes it resource intensive. Is to help them break through the ways of thinking about mathematics and about learning mathematics that they developed in high school. Well, elementary school and high school. Okay. And then I have a number of research questions, but I'm already getting to the limit of time, so I'll not share them. But again, they're on the webpage, so let me scroll all the way to the end and say thank you.